Hello, everybody. This is going to be our video lecture on ReadWriteLocks. So first, let's dig into the quiz. There's a couple of parts to this quiz. First of all, we're going to have, I want everyone to imagine the dining philosopher scenario we discussed the other day. So this was first presented by Dijkstra in 1965. It was an exam for students. In this situation, you have 5 philosophers sitting around the table, and they alternate between thinking and eating. And they do a lot of time thinking, a little bit of time eating. This is analogous to sort of how a process will go between using the CPU and every now and then needing an I/O device, like what was in 1965 a tape drive. You can think of it as a disk drive or the network or a printer or whatever. In this implementation, the philosopher, each process would acquire the chopstick to their right, then acquire the chopstick to their left. Once they have both chopsticks, they can eat. And to be very clear, it's fine for someone to have to wait. So if like Descartes here has to wait on, I don't know who this is, some philosopher here, it's fine for them to wait. They'll wait until they're done. Once they can get both chopsticks, they'll eat. And then when they're done eating, they will release those locks and go back up to the next round. And so this is sort of the life of a philosopher, just alternating between thinking and eating. The first question is, how can this implementation produce deadlock? And the second one is, I want everyone to think of multiple different approaches of how they can change this implementation so that they can prevent deadlock. When you're done with that, there's a read-write-lock situation where we're going to talk about that. And I want to talk about read-write-locks in the context of a concurrent map. Okay, this is going to be very near and dear to your heart as you're going to have to build one. But the first question is, which lock should you use, the read, the write, or neither for something like compute? Okay, and look up map compute if you don't know what it's doing. Which one read, write, or neither should you use for get, and which one read, write, or neither should you use for put? When you're done with that, I want you to think about different approaches for locking to make a map thread safe. So the first one is lock the entire map. So how would you achieve this? And then 2, what are the performance implications? Locking the bucket for a specific key, okay? How would you achieve this? And what is the performance implications? And then locking an individual entry. So this would be, so locking the whole map, locking a particular bucket, and then locking, say, John Smith versus Sandra D in this example. So how would you build each one of those, and what are the performance implications? All right, and we're back. Hopefully you all dug into that. Let's sort of talk about this. We mentioned this a little bit before, the dining philosopher's problem. It's a great problem. It's one of the first things that I did in my operating system class way back in the day. So how does this produce deadlock? This can happen if every single philosopher happens to grab their right chopstick. They will hold that lock, okay? And then they all move on to try to grab the left chopstick. Meanwhile, the philosopher to their left has grabbed their right chopstick, right? So all the resources are taken. All 5 philosophers each hold one chopstick, and all of them will wait forever because none of them are going to drop their right chopstick, so no one will ever be able to pick up their left chopstick. Okay, so let's talk about some different ideas. Hopefully you came up with some of these. First of all, a lot of times these are ideas brought up in the class in previous semesters. Add more chopsticks, right? You get this bonus of it's more hygienic, so that's nice. Everyone you just imagine, all right, well, I'll just add it so that I'll add 5 more chopsticks so everyone can have their own chopsticks and we have no more problems. That is true. Actually, you only need to add 1 more chopstick to prevent the cycle. This is a little unrealistic. This is kind of like saying every process would get their own disk drive, and every process would get their own printer, and every process would get their own network, right? And so this will definitely solve the problem, right? You can't have a cycle, which is what you require to get deadlock. And so if you just add more chopsticks, you're fine. Another one is to shoot, let's say shoot Socrates Johnson, as I believe he was called by the Wild Stallions heroes, but also Socrates or Socrates. And this has upside or downside depending on if you're Socrates or depending on how you feel about it. This would also solve the problem, just kill one of the processes. Then you only have 4 philosophers and 5 chopsticks, and you can no longer deadlock. That's also not what I would call a long-term. That's not really what we're looking for, but it would solve the problem. Another one is to have one lock to rule them all. You can either have just one lock and have everyone just always just lock on that. So instead of having each one go to the right, left, right, you would acquire the lock on, say, the rice bowl, and then you would grab them both, and everyone would do that. And so what would happen there is no two philosophers could eat at the same time. But there would never be deadlock, right? Because whenever anyone was eating, everyone would wait that person. And that's better than deadlocking, to be clear. But if Confucius and Socrates can eat at the same time, why shouldn't we allow that, right? So that's definitely worked. There's another variant on this where there's you have a lock which holds, you acquire it, pick up both chopsticks, and release the lock right away. So it only protects the part where you're picking things up. You would need an explicit lock for that, but that could be done. But that's another variation of this, is just protect the picking up of the chopsticks moment. Another one is you could try to get both, and you can't build this with synchronize that we have here, right? But you could do what's, there's something called try lock in Java. There's I think in a lot of languages that have this. Try to get them both. So try to get the first one. If I get it, press on. Try to get the left one. If I fail, drop them both. Like, I didn't get this one, so put this one back down, sleep some random amount of time, and then try again, right? So this would also prevent deadlock. We will build this in our second studio. My personal favorite one is to just make one of them left-handed, okay? So if 4 of the philosophers go right, left, and one of them picks the left side first and then the right side, then we can no longer have a cycle. And that is, I believe, the simplest way to solve this problem. It works like a charm. To be clear, like, you might wait for somebody, right? There's nothing wrong with that, but you'll never deadlock if you do that. And that's a very simple ordering thing. You just have an ordering of the chopsticks, and everyone always picks them up in that order. And then you can't have that cycle. So if you imagine 0, 1, 2, 3, 4 is the philosophers, and these are the 0, 1, 2, 3, 4 chopsticks. This guy over here would grab left, right, if you will, because 0 would be less than 4, and everyone else would go 0, 1, 1, 2, right? Just a very simple ordering can usually fix that problem. To talk about the read-write locks, compute would grab the right lock, get would grab the read lock, and put would need to grab the right lock. That's because compute and put both mutate the data, and get does not. Okay, let's talk about this a little bit further. For a thread safety perspective, to lock the entire map, you could simply synchronize on the entire data structure that was the map, or hold one lock, whether it was explicit or implicit, and lock that. The performance implications are that, first of all, it would be correct, so that's good. The downside is, every single time you try to call put or get or whatever, everyone would have to wait, so it would turn it into sequential, right? So it'd be correct, but you'd be like preventing mutual access to your data structure all the time. Like, anytime two things, you wanted to access 2 keys, either for put or get or compute, everyone would have to wait. By locking on the bucket for a specified key, how do you achieve this? Well, instead of locking the entire object, you would just lock the list in this one bucket, right? The performance applications here are kind of nice. I don't have to change the data structure at all. Like, I want to build the hash table like this. I already have lists here. Instead of locking the entire object, I just lock this one bucket, right? And so if all of these guys were going in parallel and everyone was doing this, these 4 or 5 could go totally without interrupting anybody, right? Then no one would be in anybody's way. And John Smith and Sandra D would have to wait for each other to finish, right? Like, one of them would get there first. Like, let's say John Smith goes first, Sandra D would be like, oh, I gotta wait, right? But meanwhile, Lisa Smith and Ted Baker and Sandra, everybody else is working perfectly in parallel with each other, and everything's fine. For locking the entry, that is a little bit trickier to pull off, but can be done. There's something called hand-over-hand locking, where you would sort of like, as you were running down the list, you would acquire and release the locks as you go. And that can definitely be done if you needed that. If you're looking for what is typically done or what concurrent hash map does, it's definitely working this like locks on the buckets. It actually makes fewer locks than buckets, so a particular lock will protect multiple buckets. But it's definitely doing this, like there's already the structure of the hash table already leads itself to this style, so it just does that. It doesn't bother with hand-over-hand locking, and it seems like a pretty good decision, if that makes any sense. Get to some synthesis and questions. How do I choose read or write? Basically, it comes down to, are you mutating the data or not? If you're mutating it, you need to grab, oh, yeah, this is read or write. If you're mutating the data, you got to grab the write lock. If you're not, like if you're just reading from get, you can grab the read lock. Why would that give you more parallelism in this case? Why does the read or write? Because if you get the situation where everyone's reading, then you have nobody waiting on anybody. And this is not the most obscure state, sort of state of affairs or situation. A lot of times data structures have this pattern where there's sort of you build it up and there's rarely any writes. So like there's few puts and a ton of gets on said data structure. So if you have a data structure that has that pattern where there can be just a lot of reads of the data structure and sometimes you have writes, this reader-writer separation can be worth it. Again, why can D&E run simultaneously? Because they're both acquiring the read lock, right? If, to be very clear, if F comes in here and does something, like everybody's got to wait, right? But if you just had a bunch of people calling D&E, they could be fine, right? Y is remove, acquiring the write block because it's mutating the data. Hopefully by this, at this point, it's kind of clear. There was a bunch of questions. There was one on Piazza too of like, why are these the same? It's literally like isolated is implemented to simply call isolated with write mode as its default. It's just, they're the same thing. It's just a well-chosen default, I'll say. That when, so that if you just want isolated, the sort of natural default is to be the more restrictive of the two. And let's talk about that. Like, why is that the default and not read mode? Like, if read mode is so much better performing, why not make that the default? Okay. And so with that, I want you to imagine the following scenario. I want you to imagine that you are in charge of protecting this track, right? So it's like your summer job, and you've got this internship, and they're like, okay, so we've got this train tracks. The two of them come together in this rather narrow section, and we need you to protect this section. And just as a heads up, as I said before, these are semaphores, and that's where the name comes from. There's a lot of really good analogies to protecting, it's not a stretch at all to think about protecting this as a critical section of track, right? Multiple processes, let's call them trains, are going to be using it, and we really don't want two of them to access it at the same time, okay? And so you're concerned, naturally, that you've been tasked with this job because you don't want two trains to crash into each other, and so you call tech support and they say, don't worry, just use the prevent train crash method. And you're like, okay, good. And so like you use that, you feel all good, and then this happens, right? And so you call them back, and they're like, oh, like prevent train crash like defaults to read mode. The documentation clearly states that you will prevent you from crashing into another train, but not them from crashing into you. You should have used prevent train crash. Seriously, I mean it. Or like write mode, you can imagine here, right? And so in all seriousness, like this, I looked this example up the first semester I taught it back in 2016, and literally that summer there was a train crash in Italy. They continue to happen where where 23 people died and 52 others were hurt. Like in the modern, and like in 2016, like trains are still crashing into each other, right? And so this should not be happening anymore, and it still does. And one of the things is that Isolated exists to protect critical sections, and write mode is default, and it should be, right? The idea is that by default, I want to make it so that only that this is thread safe. And I've got to go through a little extra hoop to say like, oh, by the way, this is get. And so like it can be read mode, right? And that's the way the default should be. Some other questions. Is again isolation similar to synchronized? Yes, object-based isolation is the closest cousin to synchronized, and also is read is similar to ReadWriteLock? Yes. So ReadWriteLock, since JDK5 is the closest cousin to write isolated, you'll be using that in your Lab 5. Just some questions. Am I correct in assuming that like these kind of practices are already implemented with ArrayList? Like absolutely not. No, they are not. They literally say in their note this implementation is not synchronized. And usually this is a common thing. They'll make one that's faster, has lower overhead, and is not thread safe. And then they'll give you something like concurrent link queue or concurrent hash map that uses isolation's cousins like synchronized lock, explicit locks, and atomics to pull off thread safety. Okay. Isn't there technically nothing wrong with doing put operations in parallel with hash? Like, no, everything is wrong with this. Like, this is not good. Hash map cannot handle concurrent writes. You can lose information. It can crash. They say you must, if you want to do this, synchronize externally. Concurrent hash map is safe, so they do have a version, like I was mentioning, that is thread safe, although you can still have the atomicity race for get then put, as we know is not atomic. And then, all right, again, the concurrent hash map does make it so you won't lose anything. Excuse me, there's still the atomicity race, but the internal structure might be different, but that's less important on a hash map a lot of times. Can there be a data race with isolation? Absolutely, there can. I want you to imagine this situation, right, where we say like, oh, I'd like to use it as read mode, right? And I'm literally mutating it, right? There's nothing magical. It's not going to look. No one is ever going to be analyzing your code. You might be able to get something that tells that you have a data race, but short of that, nobody is going to. It's not like when you say isolated and do read mode and then write to it, you're going to be. They're going to let these three things happen simultaneously, right? Because you literally told it, oh, by the way, I'm only going to read and then write. You could also protect the wrong data structure. So, for example, if you were doing things on shared mutable data and you isolated on some other object. So like, let's say these two isolated on Fred and this one isolated on George, and they were all mutating the same data, then you can have a data race. If you use isolated correctly, you'll be much less likely to have a problem. The analogy I like here is that the reunification express in Vietnam, I've never been on it. What I know about this is that the North-South Railway in Vietnam is a single track system. So how they keep trains from crashing into each other is they have these physical keys. And so for each station along the reunification express, there's a key. And when a train comes in, if the key isn't there, the train waits, right? And when the train coming, let's say, from north to south shows up, that train hands off the key, and then they give it to the other train who goes the other way, right? And so this physical key, everyone agrees to acquire it before they go onto the track. This keeps trains from crashing into each other. What I like about this analogy a little bit even further is that if there's nothing magical about this key, it's not like if you hold this key, no one will crash into you. Because if some other train isn't well behaved, they can crash into you, right? So everyone has to behave well, right? If 10 tasks all acquire the lock correctly, and an 11th one is a chucklehead and just doesn't use isolated, right? They can crash into the other ones, right? And so you can write perfectly thread safe code, and your thread could still be the one that throws the exception, right? And this is part of why concurrent programming is so hard, is that someone else is messing up your day. and that can easily happen. I'm not entirely convinced that isolated works. If it affects the sequence in which tasks are done, how can it ensure determinism? It doesn't ensure determinism, but so it's non-deterministic, but a lot of times that's okay. And so it all depends on what correctness is. Sometimes I don't care what order the list is in, as long as no one gets lost. For example, the concurrent link queue we used to keep track of futures in X quicksort. For all the tasks, you just need to add them. I don't really care what order they're in. I'm just going to pull them out and call get on them, right? It's really critical to me that you don't lose any of them, right? And so concurrent link queue is good enough if all you want to do is not lose anybody, right? And when you're doing things in parallel, a lot of times you're giving up the ability to control what order they're in. Like by definition, you say they can run in any order, right? And so data structures like this are nice, even if they're non-deterministic. Oftentimes they have sort of properties that can keep you to be correct, which is important. Let's talk about intrinsic and explicit locking for a quick second, just to compare the two of them. So if you have some lock and you do object-based isolation, that's a lot like getting the intrinsic lock of some object via the synchronized construct. A lot of people hopefully are familiar with this ticker class from CSE 247, where they had this long, this is a not thread safe class. You could make each one of these methods thread safe by doing synchronized on them, okay? And even this get would need it just for memory visibility, which is another aspect of things where it's just, you just have to protect all the reads and writes to a particular field. This is the shared mutable data, the tick count. You can also make a lock. You don't have to synchronize on this. That's the object, the current instance. You can make an object that you want to do that on, which works just as well. And that's the intrinsic lock. So every single object has its own lock associated with it that you can get. They also have explicit locks. There's a lock interface. You can create instances of it, including reentrant lock. There's, we'll talk about read-write locks in a second, but there's reentrant read-write lock, right? And how this works is you can create one of those locks that I just showed instances of, and you can call lock, do something, and unlock, right? And there's a bonus problem of whenever, let's say, do something through an exception, right? Then we would never give up this lock, and that would be a problem for other people. There's a fantastic feature in Java. A lot of other languages have a feature like this, where you can do try, do something, and then no matter what happens, like if something returns from in here, it throws an exception. No matter what happens, it will run the code in final. So in this case, if do something through an exception, do something else would never happen. And so what you'll do is do something like connect to the database, do something, and then no matter what happens, disconnect from the database. Also closing a file. This is a really useful feature to use in a lot of ways. And one of the things that comes up is this, well, I've acquired a lock, no matter what happens, unlock. And so all of your implementations in this class, as well as for your entire life, anytime you acquire a lock, it should be accompanied by a try finally, and the finally should unlock it. So this is what the ticker class would look like in this situation. A tick would acquire the lock, do this, do the work, and then in a try finally, it would do the work and then unlock. As far as the reader-writer isolation, there's a read-write lock. That's an interface. It has a reentrant read-write lock as its one of its implementing classes. And this has the read lock and the write lock. And so in this case, there's one explicit lock. And for tick, these two ticks, they're both mutating data, so we need to acquire the write lock. And the get tick count acquires the read lock. To be very clear, you never want to grab the read write and read lock. Let's say you're reading and writing, right? You don't grab the read lock and the write lock and lock them both, right? Like, first of all, that will likely lock you and you will be deadlocked. Just pick one of them and go. And so the write lock you can think of as the read lock plus, right? So if you're ever going to be reading and writing, just grab the write lock, right? And don't transition from reading to writing, if you will. Don't like grab the read lock and do something. A lot of times you've created an atomicity race in that case. Just pick the most appropriate lock, grab it, and hold it for all of your work, and then unlock it. As a side note, this ticker could also be well built as an atomic long, and I leave that code here for you. But seems like a simple case that can show off all the examples, but I didn't want to leave off atomic long because that's a perfectly fine implementation of atomic. How can we use this, to complete Lab 5? Of course you can. Like, we're going to build a concurrent bucket hash map. You're going to need to use the read-write-lock for this for each bucket, and it should. It's a well chosen example for this. This is you're going to build something that is very similar to how the overall structure of how concurrent hash map is built. It makes perfect sense to have locks protecting your buckets. Okay. And with that, I'm going to point you to the video I shot separately of just how to do the lock ordering studio, which is going to be today's studio. And I've left the slides in here for your benefit. But just if you haven't watched this, watch this now. And good luck and have fun on the studio and the lab.